So welcome to the first lecture of chapter 3. So chapter 3 will also be partitioned over 2 weeks, and I guess in total I will need about 4 or 5 lectures of each half an hour. And so what we're going to do, we're going to look at chemical reactions. First chemical reactions and then biochemical reactions. Biochemical reactions are reactions that are catalyzed by enzymes, and chemical reactions are spontaneous. So let me start with a very simple reaction just to get a feeling for it. So we have a reversible reaction now. So S is converted into P and P is converted into S. So S in and P are different chemical compounds. They can spontaneously interconvert. Okay, so that means that if I would have a test tube with some water in it and I would only add S, then over time S would go down and P would be made. Okay? So for each molecule of S, one molecule of P is made. Okay, so whenever you lose one molecule of S, you gain one molecule of P. So that must mean, right, that minus ds dt equals dp dt. Because ds dt is the slope and dp dt is the other slope. So ds dt is going to be negative because you're losing S, and dp dt is going to be positive because you're gaining S. But this relationship has to be true. Okay, the value of the loss of S and the gain in P is going to be called V, right? And that's going to be the rate of the reaction. So the rate of the reaction just tells you how many molecules of S you lose, or alternatively how many molecules of P you gain per unit time. It's the rate of the reaction. Now the rate of the reaction V, right, has a forward component, V plus, and it has a backward component. So S2P, forward component, and the backward component is the conversion of P to S. So V is positive when P is made, and otherwise negative. Because if V plus exceeds V minus, then more molecules of P are made per unit time than that you lose. So P has to be increasing. Okay, so V equals an equation. And that equation expresses the rate of V in terms of the concentration of S in P and kinetic parameters. So these are kinetic parameters. K plus, K minus. S and P are concentrations. Okay. You know that the unit of ds dt and dp dt is concentration per time. So this needs to equal K plus times S minus K minus times P. These guys are in unit concentration, so these guys need to be in unit 1 over time. Okay, so we know now all the units. We know that the kinetic parameters, these are constant. Okay, so S and P, so the concentration of S and P are variable. Okay, that is the only thing that that changed with time, right? Changed with time. Now there is one more thing to realize. And that's when I start this experiment. Okay? So if I add at time 0 S0S, but at time 0 I added no P, then I know for all future times the sum of the concentrations of S and P are going to be equal to the amount of S that I started with, right? Because for every molecule of S that I lose, I gain the P. So if I start with 100 molecules of S, I know that the total number of molecules that I have in the test tube will always remain 100, but I don't know how many molecules of S I have or how many molecules of P I have, but I know that the total amount of them is 100. So that means that the concentration of PT at every moment in time is the starting amount of S minus the amount you still have, right? So that I think is logical. So that means that if I look at this equation, then I can write S0 minus S. Now note now that in this differential equation I should have written everywhere the time dependence. Okay? I don't do that because I'm sloppy, so that's why I don't do that, but I should do that. Okay? And but every time when I look at these equations, then the concentrations are going to be variable and the K's are going to be constant. So that's why I don't do it. I know that these things depend on time, so I'm not going to be writing them explicitly as function of time. Even though I should, I'm not going to do that because I'm lazy, and most people in the field are lazy, so this is typically also not done. Right? But when you see S and P in this equation, that means the concentration of S and P at a certain time point at which you look at this slope. Because ds, dt and dP are just slopes in this bit. Okay, so if I look again at this experiment, I have S and P, this is S, and this is P. You have to think for a minute, why is it now that S is not going to be 0 eventually? Why is S going to stay constant and P also to a certain value? Why is S not 0? Well, let's say S would be 0 at the end. Then S would be made out of P, so then the concentration of S would go up again. And if P would be 0 at the end, right, then P would be made out of S. So the final concentrations of S and P equal to 0 are both impossible. So the end concentration needs to be a situation where P and S are unequal to 0. But it's also a situation, right, where, okay, P and S are constant. So that means that ds dt equals dp dt is equal to 0. There is no change in P and S anymore. So dp dt and ds dt are 0. The slope is 0. So what is then the concentration of S? Well, denote the concentration of S, the constant concentration of S now at Se. You get minus Se is 0. Using this equation, setting it to 0. And the final concentration of Se is given by this equation. It depends on the starting amount of S and the known kinetic parameters. These constant kinetic parameters. So what will PE be at the end? Well, that is just going to be S0 minus that value of Se. So I can calculate the end concentrations, because I know at the end that these derivatives, these slopes are going to be 0, so then I can solve for the unknown concentration SE. So I can calculate the concentration of SE from the starting concentration in the case, and then I also know how much P I have, because I know at each moment in time the total number of molecules is conserved. Alright, so I've calculated now these end concentrations, but one thing remains unclear. And that is, will for all starting concentration of S, will the system go always to this constant state? Okay? So will the system go to constant state with SPT and dPdt equal to 0 for all starting conditions of S. Okay, so whichever experiment I do I always end up in this final state? So that's the question. In this final state where P and S are constant. So I know that minus ds dt, right, equals V. So this equals K plus times S minus K minus times S0 times S. Okay, so that means that the SDT equals minus K plus times S plus K minus times S0 minus K minus times S. Okay, so now I can take all the S terms, I can put them together. Right, so the final equation for the SDT looks like this. Okay, and now I want to know, does the system always end up in this state where the SDT is 0? Yeah? And I'm going to use this plot to show that. So I'm going to prove to you that that's going to be true. That for all starting concentrations of S, the end concentration will be this. But first I have to plot the SDT as function of S. So you see, so this is a constant, a negative constant, so the slope on this thing is going to be negative, so it's going to go down. And I have an intercept, a positive intercept. And I know it's a line, because this function depends linearly on S. Okay, so there is no S squared in it, or 1 over S, or the sinus of S, it's just S, so it's going to be linear. So I know when S is 0, I have K minus times S0, and I have a line, so I need to know 2 points, so I can figure out the value of 1 point, that is when the SDT is 0, so when this is 0, right, when the SDT is 0, then I obtain the equation that I already derived. I obtain the eventual value of SE. So that's sitting there. Right, and the curve is going to look like this. Okay, so there is a part, so on the left from the final point, the SDT is positive. And on the right from this final point, the SDT is negative. So if I would start, if I take a concentration of S here, then the SDT is positive, so S is going to rise, right, until you end up here. If I take a concentration of S here, then I know that the concentration of S that I have, right, will go down because the S dt is negative. So for all values of S greater than SE it will go down, and for all values of S smaller than SE the concentration of S will go up. So the system will always go to this end state where P and S are constant. Okay? So will the system go to the constant state with ds dt and dp dt is 0 for all starting conditions of S? The answer is yes. Yeah, that will happen. Okay, so this trick, what is called the stability trick, we will use a ton of times, a million of times in the syllabus. So this is something that we're going to do plenty of times, so we'll have plenty of opportunity to practice. Okay. So summarizing, we have slopes, or sometimes called an ordinary differential equation, or a rate of change, or a mass balance. We have rates of reactions that can be described in terms of kinetic equations or rate equations that have rate constants in the case, and they depend on concentrations. Then ds dt and dp dt are slopes in these curves. And this system, in this particular case, ends up in a state where the concentrations of S and P are constant. So the final state of a constant S and P concentration, where none of them equals 0, so both are unequal to 0, will always be reached in this system. Okay? So I hope now that you memorize what I did here. Okay? And I hope that you memorize the terms also. The rate equation, differential equation, mass balance, rates of change, kinetic constants, all these terms should be clear. Yeah? Now the final thing that I'm going to tell you is that in this point, right, the rate itself equals 0. So V equals 0 in this point. So V equals 0 in this final point. So here, where this is 0, the rate is 0. Okay. Now a state of a system where the rate equals 0, or all the rates equal 0, is called an equilibrium state. A very simple definition. The equilibrium state is the state where the rate is 0. Okay. We'll stop here.